I will present some results of Balmer emission in the case of Tycho Supernova. And this work was recently published in Update, so this basically results like what I want to present. I would like to thank all my collaborators who came here, especially Ronald Masker and Balmer for who gave me support in data reduction and analysis, and John Raymond and Giovanni Morlino support from the theoretical perspective. So we already got a nice introduction yesterday on Balmer emission and Balmer dominated shocks by John Raymond. So briefly, like these are collisionless non-radiative shocks propagating in partially neutral medium. And the main signature, spectroscopic signature of these shocks is two-component H-alpha line, which is the strongest one. So you see the narrow and the broad line. The motivation for doing any observations in this field is that these shocks give an insight into physics, like shock velocity, equilibration between electrons and protons, and also shock precursors. So these filaments are very faint, so you would need an instrument that has a very good efficiency. In order to resolve the broad line component, you need a large spectral coverage. On the other hand, in order to resolve the narrow line component, which is 10 kilometers per second, you need high spectral resolution. These objects are very extended on sky, so you need a large field of view. And often have a very complex structure, so you need also high spatial resolution. So at present there is no single instrument that can do all of this at the same time. So you need some to make some compromise. So my work basically is to use the available instruments and techniques in order to minimize shock geometry contribution to these H-alpha line profiles, correct for spatial variations in the line parameters, and look for possible physical explanation. So, as was already mentioned yesterday by John, and actually, so this mechanism of producing this line was introduced by Roger Chevalier and John Raymond back in the late 70s. So once you have neutrals that penetrate into the shock, they can either be excited by the post-shock gas and produce the narrow component with a rate of 10 kilometers per second, or go in a process with a charge exchange, forming so-called broad neutrals, and produce the broad line with the order of 1,000 kilometers per second, basically the order of shock speed. So we already heard a lot about particle acceleration, and so I will just briefly mention later like how cosmic ray precursor influence the line profile itself. But there will be another kind of a precursor that I want to introduce and mention here, is that so once these broad neutrals are formed in the post-shock, they have enough velocity with a net velocity towards the upstream. They can cross the shock. They are neutral, so they don't see basically the shock, and can deposit the energy in the pre-shock region, thus heating the neutrals there and affecting the line that we see. Morlino, I found a model use the collisionless shock model, including these precursors. And as you can see here, so 0 is the shock front. Black line should be without cosmic rays. So you can see, like, if you have a broad neutral precursor, you can see how much they can heat the gas here. Of course, it's not extended pretty much, because they are pretty fast destroyed in the pre-shock region. But if you have, on top of that, if you have cosmic ray precursor, then the temperature can go much higher, up to like 10 to 7 Kelvin. and cosmic ray precursor affects larger widths that you would expect. So, like many remnants, like from 30 to 50 or 60 kilometers per second line widths, which is much larger than you would expect if the ice and temperature is 10 to 4 Kelvin. And it is explained by something non-thermal. There must be something non-thermal that can basically perturb the distribution of pre-shock neutrons and then broken the line. Also, once you have a cosmic ray precursor, so you basically have also momentum transfer in the pre-shock, and if you have inclined shocks in a projection, you would see splitted narrow line. On the other hand, I forgot to mention that I'm not going to talk about broad line component here, because with this instrument, as I said, there is no single instrument that can cover all the aspects that you need. So I observed only the narrow line and the region very near the narrow line. So I won't say anything about the effects of cosmic ray precursor on the broad line. So broad neutral precursor introduces another component, which is called intermediate line, as you can see it here, with a width of approximately order of 100 kilometers per second. And it's created due to a charge exchange in the broad neutral precursor. These models that Molino made, they also show that these kind of precursors do not affect the narrow line width. So basically, if you measure narrow line width much wider than what you would expect, then it's a signature of a cosmic ray precursor and not any other. And this is due to the basically the spacious, time and space. Broad neutrals do not have enough time and space to deposit enough energy to go to the line. You can see the zooming of this part. And you can see how the lines are affected by turbulent heating in the precursor. So the if you have higher turbulent heating, then both lines become much wider. The line widths depend on many parameters, and so having only in hand the narrow component into the intermediate, you cannot really extract some physical information. You need definitely the broad component also, which we plan to combine with these observations in order to get handle on shock velocity, temperature equilibration, and cosmic ray efficiency. So once we have the broad line component included, we apply the shock models, and then we will be able to quantify ISM and cosmic ray properties. So this is the Tycho supernova random. In red, you can see age alpha emission. We covered this part here. We also have the data from this part, but I'm not going to present them here. In this slide here, you can see an agency image of these filaments. So what is new here that we are trying to do is, first of all, to cover all regions in the filament, because previously it was only like the brightest spots, like this notch G, was covered. So using the GAFAS instrument on the William Herschel telescope, which is a Fabry-Perot interferometer with a field of view of 3.4 by 3.14 arc minutes, angular resolution of 1 arc second, spectral resolution of 8 kilometers per second, and as I said, we do not resolve the broad line because it's just the range is too small, so spectral coverage is around 400 kilometers per second. So you can see our data here, the filament itself, and so we do, according to signal to noise, we require like around 10, at least 10. So we made 82 pins. So we, for the first time, we spectrospatially resolve not only the knot G, but the entire filament. What is also new is that we introduce Bayesian analysis to estimate parameters and to compare several models. And we tested 4 models. We have like one with a single narrow line. Then in case of any kind of a precursor, as I said, you would have either splitted narrow line, so double narrow line model, or an additional line, which is intermediate line. So this is how our data look like. This solid black histogram. Dashed black line is our background model, and you can see that, and as you would expect, like different. If you just use chi-square and 3 different models, it's you cannot basically distinguish which one of those best represents your data. So you really need to do some model comparison, and that's the justification for using Bayesian analysis. So I will present one spectrum from one of the bins that we have. Again, data are in this solid black line. Our model is a solid red line. Again, background model, dashed line, and these red dashed lines are like intrinsic emission model of the source. So what we do, we use MCMC to calculate posterior probability prior. We introduced, we use several parameters, of which, like, I would just go through narrow line width and intermediate line width. I should say that for this particular location, we found that the narrow plus intermediate line model is more than 10 times likely than single narrow line and double narrow line models. So it's the preferred one. In these plots, you can see the prior distribution and the posterior that we calculate in the solid black line. We summarize these posteriors by taking the median of the distribution and the shortest 95% confidence intervals. So for example, for the narrow line limits, we use the from 15 to 100 kilometers per second range, and for intermediate line, we use the range between 100 and 350 kilometers per second. This is not just like ad hoc numbers. I mean, there is some theoretical theory behind it. And for this particular case, we find that the narrow line width is around 40 kilometers per second. We find evidence, as I said, for the intermediate line with the flux of 40% and the line width of 200 kilometers per second. So basically, the components here of the intrinsic model are shown like with the continuum, intermediate line, and the narrow line. So the continuum actually comes from the broad line emission that we do not resolve. So in our spectral coverage, it just enters as continuum emission. We do that, of course, for all the bins. And here are the maps of narrow line widths. So these are median of evidence-weighted posteriors. So here you can see the variation of the narrow line width and how flux of intermediate line varies. In this rightmost panel, you can see locations where we find significant evidence for including an additional line to a single narrow line. So in red are the locations where a narrow plus intermediate line is preferred. In blue, there's just only 4 dots here. We need double narrow line model. And in green, we have double narrow plus intermediate line. This is just another patch of the filament more north. It's the same, maps are just the same. I mean, the center is different part of the ring. And so I come to summary. I want to point out that we spectrospatially resolve the narrow line in the entire projected northeastern rim of Tycho. We used a Bayesian inference to estimate the parameters and model comparison. Here is a more quantitative summary of our results. We find that narrow line width is all over the rim, much larger than 35 kilometers per second, so between 35 and 70. So in these plots you can see the median, so histogram of median values that we measure, and these are 95% confidence intervals in blue and red. So we find superthermal narrow line widths. In 18% of the bins we find significant evidence for double narrow line, which are also even, the line is splitted, they also have superthermal widths. And we think that this is a clear indication of presence of a cosmic ray precursor. Next, we find that we need an intermediate component in 24% of the bins. We find on average that the line width of the intermediate component is 185 kilometers per second, with the flux fraction, intermediate to narrow flux fraction of 0.4. And this is a hint or confirmation that there is a broad neutral precursor. And thank you for the attention.
So before the end of it's finished, please, questions?
Very nice work, thank you for a nice presentation. Related to this background subtraction, if you could just go like 2 slides before, since you have a very low, with very low spectral coverage, I mean, how do you estimate the background?
So we have a very large field of view. So all over the field.
So from the field, basically?
Yeah.
So no like some...
No, so from the field. And what we actually see is so you have contribution from, so H alpha, this is the H alpha and nitrogen line, galactic lines, and also you have geocoronal lines, like which are part of this one.
No questions? We have no time. No? Please.
Can you tell us what do you mean by superthermal? Because you're talking that this region
Superthermal. So everything that is broader than 20 kilometers per second.
But how do you model them? Is it the power law? Or?
No, it's a Gaussian lines.
Yes, but what produces them? What produces the Gaussian lines?
The width.
What distribution of particles?
No, well, as John said yesterday, we use that assumption that it's like this way.
So even these superthermals?
So, yeah, in principle, I mean, like, even this, like, for example, this intermediate line, it's not Gaussian. Right? But you really need the good data to, in order to try to fit anything else than a Gaussian, which we do not have, and I don't know that it actually exists. So we are happy, like, with the Gaussian, which is not exactly the right approximation. Yeah, it's the easiest one.
So, more questions? Please.
What's the number which is much higher than 21 kilometers per second?
That you get from our data?
Yes.
72 kilometers. So 70.
Thanks.
So I have only one comment. It would be very nice to have the errors with the numbers which comes here.
So the only number, yeah, okay. But you can see basically from the, so since we quote 95% confidence, so it's a very large number, right? So, but you can see them in red here.
Okay.
Red line, yeah.
But every measure the value need.
Yeah.
Please put it.
So when you say velocity, you're basically, this is like the velocity dispersion, right? From estimates from the line.
Yes.
Thank you.